It's chemistry and you are watching Chem Science.
In this video, let's solve question paper 2-2 of the examination series 9701 chemistry May-June 2024, and in this video we'll be solving half of the question paper, and the remaining video, the next video, will solving the remaining questions. So let's start with question 1 here. It says complete table 1.1 using relevant information from the periodic table. So using the periodic table, we can check the question here and fill up the table where it says Mg2 plus and Al3 plus, that is magnesium ion and aluminium ion, are given here. The nucleon number is given here, and we are supposed to find out the proton number from the periodic table. And the proton number of magnesium is 12 and aluminium is 13, and number of electrons, if we check, there are 12 protons and 12 electrons in a magnesium atom, but here is an ion with +2 charge, that is 2 plus ion, so 2 electrons are less, so the number of electrons are 10 here. And same in the case of aluminium where 3 electrons are less, so 10 electrons again in the aluminium ion also. Let's go ahead with the next part. State and explain the difference in the ionic radius of Al3 plus, that is aluminium ion, compared to the magnesium ion. Now what's the difference? We can find out that the number of electrons are same, so electronic structure is also the same. The difference is in the proton number. So what is the difference in the ionic radius? Now obviously the ionic radius of aluminium ion should be smaller. The reason being is that there are more number of protons, so the nuclear charge is higher, and the same number of electrons are attracted as compared to the magnesium ion, but as the proton number are more, the attractional force will be greater, that will squeeze down the atomic size, ionic size. So what's the difference? The aluminium ion is smaller than Mg2 plus, that is magnesium ion, as the nuclear charge, or you can even write that the proton number is higher. So nuclear charge in Al3 plus is higher. The number of electrons are same. Number of electrons are same. Shielding effect is same. Shielding effect is also same because the inner shells are same. You can say that there are only 2 electrons in the inner shell, which is shielding the attractional force. So because of that, the attractional force between the nucleus and electrons is greater in aluminium ion, so that's the reason that the ionic radius of Al3 plus is smaller than the Mg2 plus. Okay, the next C part, it says draw a label diagram to show the structure and bonding in sodium. Now sodium is a metal, so the bonding in sodium is metallic bonding, and so what do we need to draw is the positive ions in a regular lattice structure. So the size of the positive ions should be actually similar, so you can use even pencil to draw the same size of positive ions. All these are positive ions which I have drawn, and you can see there is a regular lattice structure, means the positive ions are arranged in a regular pattern, it's not an irregular pattern, and surrounding them is a sea of delocalized electrons. Here we have to draw the delocalized electrons all around the positive ions, and these delocalized electrons, we know that there is a very strong force of attraction between these delocalized electrons and the positive ions, and that's the reason that the metallic bonding is very, very strong. So here now we need to label it that these are the positive ions, and here are the delocalized electrons. Now why do we call them as delocalized electrons? Because these electrons can move in between the lattice structure, so that's why we call them as a delocalized electrons. Now the D question is, figure 1.1 shows the variation in the melting point on some period 3 elements in their standard states at room temperature and pressure. So here are the some elements shown here, and the melting point on y-axis are shown. So we can see that the melting point is increasing till silicon. Now let's see what are the sub questions following it. It says, explain why silicon has a high melting point. Now compared to the other elements, silicon has a very high melting point, which is crossing 1500 Kelvin. So if we talk about why the silicon has a high melting point, though for when we are talking about melting and boiling point, we need to think about the structure and bonding. Now what is the kind of bonding present between the silicon atoms in silicon element? Now silicon has a giant lattice structure, giant covalent structure, I'll specify here. So we can explain here that silicon has a giant molecular, or you can even write covalent structure, giant covalent structure, and there is a strong, there are strong covalent bonds in the structure which needs high temperature, which needs, even you can write high energy, which needs high energy to break down, and that's the reason that the melting point of silicon is very high. Now this is just 1 mark, so you can even explain them in short, but I feel if there are 3 lines enough, we can explain it in good explanation. So complete figure 1.1 to show the variation in the melting points of elements of phosphorus, sulfur and chlorine. Now we need to understand that after silicon comes phosphorus. Now phosphorus as an element exists as P4 and it's a non-metal. So it has a simple molecular structure. So obviously it has melting point much lower than even sodium. So we just need to draw a straight line which is even lower than the sodium. Now my straight line is not going as I'm not using the scale, but you can use the scale and even draw it in such a way that it is lower than the sodium. Now compared to phosphorus, the sulfur has a S8 structure. Sulfur exists in a ring structure with 8 atoms all together. It will form a ring structure with 8 sulfur atoms this way. And so the van der Waals force between the 2 sulfur molecules will be greater than the van der Waals force existing between 2 phosphorus molecules, which is P4, because the atoms here are P4 only, so the electrons are less. So van der Waals force is also less in phosphorus. But sulfur has more number of atoms, so more electrons and higher, stronger van der Waals force. So compared to phosphorus, the sulfur has a little higher melting point. But then chlorine exists only as Cl2, that is diatomic structure, which has a very low melting point. It exists as a gas at room temperature. So we can draw the line still going down. So this is how we are going to complete the graph of the melting point of the remaining elements in period 3. Now let's go ahead with the next question. It says 2 period 3 elements react with excess of oxygen at room pressure. Complete table 1.2. Now what is the table 1.2 is that period 3 elements are sodium and sulfur is shown. The state of oxide at room temperature and pressure. So what's the oxide of sodium? The oxide of sodium is sodium oxide, that is Na2O, which is an ionic compound, and it will be solid at room temperature and pressure. So the state of oxide of sodium is solid. The sulfur is oxide is sulfur dioxide. Now that is a gas at room temperature because it's a covalent structure, so we need to write as gas at room temperature and pressure. Now approximate pH of the solution made when oxide is added to water. Now when we add sodium oxide to water, it forms a basic solution of sodium hydroxide. So the pH should be in the basic range. So we can write as 12, 13 or 14. I'm writing as at 13 because sodium hydroxide is a strong base. Now when sulfur dioxide is added to water, it forms sulfurous acid, which is acidic in nature and it's a strong acid. So in between 1 to 3 we can write any of the pH, and I'm writing it as 2 pH. You can even write 1 or 3. The next sub question, the solutions made in column 3 of table 1.1, table 1.2 are mixed together. Name the type of reaction that occurs. Now the solution made by sodium is basic, the solution made by sulfur dioxide is acidic, and if we mix the solution, the type of reaction is going to be the neutralization reaction. So the type of reaction is neutralization, or even you can write it as an acid-base reaction. Write an equation to describe the reaction between phosphorus oxide and an excess of water. Now if we are reacting, that is P4O10 with water, it's going to form phosphoric acid, that is H3PO4. Now if we're going to balance it, because here we have P4, we need to write 4 here, and the oxygen, we can see there are O10 here. Let's balance the hydrogen first. Hydrogen goes 12, so we can write 6 here. Now if we count the oxygen is 16 here, and on the left hand side also the oxygen is 16, so the reaction is balanced here. Okay, the next part is aluminium hydroxide is amphoteric. Explain what is meant by amphoteric. You can describe amphoteric substances as the substance which can react with both acid and base, with both acids and bases. So amphoteric substances reacts with both, so you can say that it has both acid and base character. Now write an equation to describe the reaction that occurs when the aluminium hydroxide AlOH thrice reacts with NaOH. So you're going to react aluminium hydroxide, which is amphoteric, that's going to react with the base, that is NaOH, and it's going to form a complex salt. Its formula is NaAlOH 4 times. So you need to remember the formula of this complex salt. Here the question 1 ends. Let's go ahead with question 2. Separate samples of sodium carbonate and sodium hydrogen carbonate react with the hydrochloric acid to produce the same products as shown in table 2.1. So here you can see that the sodium carbonate and sodium hydrogen carbonate both are reacting with hydrochloric acid to form the same products, that is sodium chloride, water and carbon dioxide. With the enthalpy change, that is delta H, values are going to be different for both the reaction. Now let's see what are the sub questions following it. It says complete the reaction pathway diagram in figure 2.1 for reaction 2. Label the diagrams to show the enthalpy change delta H2 and the activation energy EA1. Now if we are talking about the reaction 2, that is the reaction 2, here we can see that the enthalpy change is a positive value, that is an endothermic value. So for an endothermic value, the product has a higher value compared to the reactants. So let me draw the level of the products again, as because it has gone slant, and now they have told us to show the activation energy. So its bump is going to be the higher. Again, I've drawn it little zigzag. Let me draw it again. Okay, I've drawn it little better. So now what is reactants are already written on the reactant side. So we need to write the products on the product level, that is H2O plus CO2. That's how we're going to write, and they told us to label the enthalpy change and the activation energy. So enthalpy change, we have to draw it from the level of reactants to the level of the products, that is delta H2, and activation energies from the level of the reactants to the bump. That's an arrow you're going to write. Now this is EA, that is activation energy. This is how we are going to label it. So this is how we have completed the diagram. The next question is, the value of delta H1 is determined by experiment using the following method. And the method is shown here, that the 50 centimeter cube of 2 moles per dm cube HCl is added to a polystyrene cup. So hydrochloric acid is added in a polystyrene cup, and the initial temperature is recorded as 19.6 degrees Celsius. In that solution of hydrochloric acid, 0.04 moles of sodium carbonate is added, and the mixture is stirred. All the solid sodium carbonate disappears, and the colorless solution is produced, and the maximum temperature is recorded as 26.2 degrees Celsius. Now describe one other observation that shows that the reaction is complete. Now what one other observation? The first observation is that the solid sodium carbonate disappears. That is the first observation. What is the next observation? Now we need to understand that we are adding a carbonate to an acid. Now whenever a carbonate is added to an acid, carbon dioxide gas is produced, so fizzing or effervescence is seen. That is the observation. Now if fizzing is seen, then that is the observation that shows that reaction is complete, is that when fizzing stops, then the reaction is complete. That's how we can make out that the reaction is complete. Okay, let's see what is the next question. Fine. Now calculate delta H1 in kilojoules per mole. Assume the specific heat capacity of the reaction mixture is same as that for the water, and no heat is lost to the surrounding. Now if we talk about the formula, it is Q is equal to minus MC delta T. Now here M is the mass of solution or the water we have used, and the amount of solution we have used is 50 centimeter cube. Now 1 centimeter cube is equal to 1 gram if we talk in general. So mass is going to be 50. And the specific heat is 4.18. So here specific heat we have mentioned. Now delta T is the temperature change. Now temperature change is 26.2 minus 19.6, because that's the temperature change from final to initial. So the temperature change, the difference is 6.6. So that's how we are going to write. And the answer is minus 1379.4. Now this is the joules because the specific heat is accordingly. Now it is the only heat produced during this process. Now they have asked us to find out the enthalpy change in kilojoules per mole. If we want it out, want to calculate for per mole, then we need to find out the enthalpy change, where we are going to divide the energy change by the moles, amount of moles, and the amount of moles which we have used for sodium carbonate is 0.04 moles, because that's the limiting reagent. So we'll divide it by 0.04. Now again we are changing joules into kilojoules, so again we'll have to divide it by 1000. So if we divide, we get the answer as minus 34.5 kilojoules. So here our answer is minus 34.5 kilojoules per mole. That's the enthalpy change. Now here we have next, thermal decomposition occurs when sodium hydrogen carbonate is heated. Now this is the equation shown. Calculate the enthalpy change for the reaction 3, that is this reaction. delta HR using the table in table 2.1, that is a data in table 2.1, and the value delta H1 calculated in B2. Now if you are unable to calculate delta H1, then they have given us the value, but let's understand and the whole process. If we have written a reaction like this, and it's Na2CO3 plus H2O plus CO2, this is how the reaction is. Now we have already seen that there is a cycle where on reaction with HCl it produces sodium chloride, water and carbon dioxide. That is the products it forms when it reacts with the hydrochloric acid. That's the same sodium carbonate again when reacts with the hydrochloric acid, again it produces the same products, but then here we have imbalance 2. Now here also we have 2, and so we need to write 2 in all, and so this is how we get the products. Now if we talk about delta H3 of this reaction, the energy cycle, or you can say Hess cycle if you want to calculate, then we can see that this is the indirect path and this one is the direct path. Now the reaction value for the direct path is given here in the table, which is plus positive yes, let's see, it's positive 27.2. so if it's positive 27.2, we need to multiply it by 2 because here we have taken twice the moles which is used in the reaction as in the table. Here we have calculated minus 34 point, let's see what is the value we have calculated, minus 34.5. That's what we have calculated in the earlier experiment. So if we want to calculate delta H3, we need to have it the direct minus indirect value. So we have 2 into 27.2 minus of minus 34.5, and we get the value as plus 88.9 kilojoules per mole. So our value is positive 88.9 kilojoules per mole. We need to mention the sign wherever possible because in enthalpy change positive and negative, that's the sign matters. Let's see what the next question says. Z is a salt that contains period 4 element from group 2. Now it's a period 4 element. We can see the periodic table to check which element is present in group 2 and period 4. When Z is heated, a brown gas is formed. Identify the formula of the Z and use it to write an equation for the reaction here. Now the period 2 element which is group 2 element which is in period 4 is calcium, and its nitrate they have written. The Z is heated, brown gas is formed. Now Z is a salt that contains, now that as a salt which is heated, it produces a brown gas. Now brown gas is nitrogen dioxide. Nitrogen dioxide is a brown gas. So what's the salt which is heated? It should be calcium nitrate. So the formula of the calcium nitrate is CaNO3 twice. Now when that is heated, it produces calcium oxide plus nitrogen dioxide plus oxygen. Now if we balance it, we need to add 2 and 2 and 4. Yes, this is how it's balanced. You can even balance it otherwise by just adding half here and 2 here. That's how you can also balance. This is how I prefer balancing. So here our question 2 also ends. So let's start with question 3. Now it says describe what is meant by dynamic equilibrium. Now if we talk in terms of equilibrium which is dynamic, then we can say that it is the reversible reaction in which rate of forward reaction is equal to the rate of backward reaction. backward reaction, means both the reaction is going on at the same rate, at the same speed, and that's why the concentration of reactants and products, the concentration of reactants and products remains constant. That's how we describe in dynamic equilibrium. Now let's go ahead with the next part. Says reaction 4 describes the reversible reaction between yellow Fe3 plus ion and colorless the SCN minus to produce a red ferric cyanide, you can say FeSCN2 plus aqueous complex. Now reaction 4 is given here, and here are the complex and the reactants given here in the form of 2 ions. And we can also see that the Fe3 plus in the aqueous form, that is ferric ion in the aqueous form, is yellow color and the product is red color. Now the question is, an equilibrium mixture contains Fe3 plus and SCN minus and the complex. A few colorless crystals of the soluble KSCN are added. That is, we are adding this in the more form. Now the mixture is then left until it reaches equilibrium. So a new equilibrium is established again. Now the temperature of both equilibrium mixtures is the same. The first part says deduce the changes that occur if in the equilibrium mixture after KCN is added compared to the original equilibrium mixture. Now if we are adding KSCN solid to the form, that shows that we are increasing the concentration of one of the reactant. Now if the increasing the concentration of one of the reactant to establish the equilibrium again, the equilibrium will shift right hand side, producing more product and reducing the concentration of reactant. That is how the equilibrium will move. So change in the appearance, now that is the first part. Now appearance will change in the sense what color it will show. Now if the equilibrium is moving to the right side, more of the product is formed and the product is red color, then the mixture should turn more red. So mixture shows darker red or more red, you can write, because it was already a mixture of red and yellow color. Now the next is the change in relative concentration of Fe3 plus aqueous. Now as we say, the equilibrium shifted right hand side, so obviously the concentration of the reactants will decrease. So Fe3 plus is one of the reactants, so we can say that the concentration of Fe3 plus ion decreases. That's what we can say, that decreases. Okay, change in the value of equilibrium constant Kc. Now we need to understand this point very clearly, that equilibrium constant Kc value changes only when the temperature is changed. Otherwise, on concentration change or pressure change, it doesn't make any difference to the value of Kc. The reason being is that the ratio of the reactants and products remains constant. The ratio doesn't change, so the value will also not change. So we can write no change in the value of Kc, no change in the value of Kc. That's what we can write. Now let's go ahead with the next part. The expression for the equilibrium constant Kc for the reaction 4 is given here, and yes, the products on the numerator and the reactants in the denominator given with the product of both the both the reactants. Okay, 5 into 10 power minus 4 mole of Fe3 plus and 5 into 10 power minus 5 mole of SCN minus, that is both the reactants are added together and allowed to reach the equilibrium. The total volume of the mixture is 25 centimeter cube. Now at equilibrium, the concentration of the product is 4.23 into 10 power minus 4 moles per dm cube. Calculate the equilibrium constant Kc for the reaction 4. Now we need to understand that the equilibrium concentration for the product is given, and here the moles of the reactants are given. So one of it we need to change and make it similar. So what I prefer is change the concentration to moles so that we get all the values in only moles. So first thing I'll do is that calculate the moles of the product, that is FeSCN 2 plus moles. Now that can be done when the concentration is multiplied by volume. Now what's volume? Volume is 25 centimeter cube. So if we divide it by 1000 to change it into dm cube, we get 0.025. So I'm multiplying the concentration with the volume 0.025 to get the moles of the product, and now that is equal to 1.0575 into 10 power minus 5 moles. That's is the moles of the product at the equilibrium. Now we know that in the reaction all the reactants and products are in the ratio of 1:1:1. So we don't need to multiply any of the values with 2 or divide it by any of the values. So here if we directly calculate the moles of reactants, then we can directly, like I'm writing Fe3 plus is equal to the moles of FeSCN minus, because both the moles are starting moles are same, and at equilibrium also they will be same because they are in the ratio of 1:1. So is equal to, and I'll directly, now what I'm going to do is subtract these value from the initial mole, because if all are in the ratio of 1:1 and the product form is 1.0575 into 10 power minus 5 moles formed, then obviously this many moles are used up from the reactants. If this many moles are used up from the reactants, the remaining we can find out by subtracting these moles from the initial moles. So initial moles are 5.00 into 10 power minus 5 minus these value to get the moles present at equilibrium. So this is how I'm subtracting, which is equal to 3.9425 into 10 power minus 5 moles. So these are the moles of reactants present at equilibrium, and here are the moles of products present at the equilibrium. So if we want to find out the value of Kc, then we need to substitute the value of concentration. So if we know the concentration of the product, we already know, so that we are substituting here, that is 4.23 into 10 power minus 4. And if we talk about the reactants concentration, then again we need to divide this value by the volume, that is 0.025, to find out the concentration of the reactants. So again, so the concentration of reactants I can write as 1.57 into 10 power minus 3 moles per dm cube. That's the concentration of reactants. So now if we substitute the value of both the reactants in the denominator, which is same, as the concentration of both the reactant is same, so I can just write square for that value, and we get the value as 170.1. Now we need to calculate the value of the units also. Now if we calculate the value of units, we have moles per dm cube in the numerator, and in the denominator we have moles per dm cube square. So this gets cancelled and only 1 moles per dm cube is left, and so the units you can write as dm cube per mole. That's how we can write. So the value of Kc is 170.1 and the units are dm cube per mole. That's how we write, and this is how we have calculated the value of Kc. The next part is determining the full electronic configuration of Fe3 plus. Now Fe is having the atomic number is 26. Now if we talk about this normal electronic configuration, then it should be like including 26, and Fe3 plus means 3 electrons are removed and it is left with 23. Now we need to understand that the electrons are removed from 4s first and then it is removed from 3d because Fe is a d block element. Now if we say 2 electrons are removed from 4s and the remaining 1 electron from 3d, then the 23 is remaining in 3d orbital. So starting with 1s2, 2s2, 2p6, 3s2 and 3p6 are fully filled. Now we are left still with 5 more electrons, so that has to be in 3d orbital. So now it is 3d5. So 3 electrons are removed in all, 2 from 4s and 1 from 3d, so it's left with 3d5 now. Okay, here is the d part of the question 3. Last here is SCN minus is a colorless substance. Now complete the dot and cross diagram in figure 3.1 to show the arrangement of outer electrons in SCN minus. Now if I make an structure, S I'm giving a dot, N I'm giving a cross, and S I'm giving a dot but not the bold. So for carbon it is a bold dot. Now carbon have 4 electrons in its outer shell. Nitrogen have 5 electrons in its outer shell. So out of 5, nitrogen should be sharing 3 to get the 8 electronic structure. So 3 of the crosses are being shared by carbon and the remaining 2 electrons are in the shell in a non-bonding area. Same with the help of carbon also. Carbon will be sharing 3 of the electrons with the nitrogen. And so it is left with only 1 electron now, which has to be shared with the sulfur. So 1 bold dot with sulfur in the sharing area. Now sulfur is having 6 electrons in the outer shell, out of which it's going to share 1 of the electron with carbon now. So it's left with remaining 5 electrons. So I'm drawing the 5 electrons here. 6 and 7 are in the sharing area, so total of 7, and it is as -1 ion, so it has gained 1 extra electron from outside, and so I'm drawing that as a bold but a bigger dot here. So that outside electron is 1 electron because it is -1, so 1 extra electron. So that's how sulfur is filled with 8 electrons, carbon also 8 electrons including the shared electrons, and nitrogen also. So this is how we are going to make a dot and cross diagram of SCN minus ion. I hope the diagram is very clear, and here question 3 also ends, and the remaining question we are going to discuss in the next video.